Welcome to the start of Precalculus or College Algebra if you're in one of those two classes or you just want to study this to get ready for calculus, which is awesome. This is going to give you a lot of background information on what makes calculus possible and the math behind doing a lot of the calculus that you might have been exposed to or have forgotten, frankly, because we all forget things, and that's okay. That's what this course is intended to do, is to teach it to you in a way that you remember or remediate you in a way that you can understand. So to start off with pre-calculus or college algebra, we need to understand what we're going to be dealing with. So the whole premise of this class is that we're going to be dealing with functions almost exclusively in college algebra and therefore pre-calculus. So we're going to discuss in this video what a function is, what makes a function, how to determine whether something is a function, and then we'll start exploring how to evaluate functions, how to find the domain and the range of functions in another couple videos. So let's start with that most basic question. If we're going to be dealing with functions, what in the world is a function? And mathematically, it's really kind of our most simple sort of an idea that we can graph. A function is something, it's this relationship that takes one input and just maps it mathematically to one output. That's it. You plug in one number, you get one number out. That's all a function really means. Now, I always tell my students face to face that sometimes we know just enough information to make it sort of dangerous, and we sort of project other things onto a definition. I'm not talking about one-to-one functions, and we're going to explore that a little bit, but keep this in mind that a function in its most basic sense and a one-to-one function are different things. So when we say a function, don't add to this definition. It's just a relationship that maps one input to one output. That's it. So we plug in one number, we get out one number. Now, when we're talking about this, we're talking about our inputs and our outputs, we're talking about functions. For this course, our inputs are almost exclusively x values, and our outputs are almost exclusively y values, or f of x, the function that's based on that x. We're going to talk a little bit about the independent variable, and we'll talk about the dependent variable as we move on. So in this lesson, the vocabulary that I want to get you to know is function, what that means, what are inputs and what are outputs, what is the domain and the range, and then this idea of independent and dependent variables. So what we've learned right now is that a function is a very basic relationship. It takes one number in, it gives you one number, or one thing, one input in and one output out. So our inputs are almost always x values. They can be different, but typically x's, while our outputs are y values or f of x values. And we'll talk about that notation in just a bit. I guess the biggest note that I want to get across right here that sticks with you is this right here. In a function relationship, a functional relationship, an input never gives more than one output. So if we start plugging in numbers and we go, all right, well, let's plug in the number 4. And sometimes this relationship gives you 7 and sometimes it gives you -2. It'd be very hard for us to graph that because it wouldn't be dependable. The output wouldn't depend on the input the same way every time. It'd be really, really difficult to graph and to deal with. It'd be difficult to count on that. So do we have these non-functions that we can graph? Yeah, we do. Typically, we use parametric equations or some other idea to graph them, sometimes different coordinates, like polar coordinates, which we learn about in like a Calculus 2 level class. But for right now, in order for us to graph things well and easily, we need functions. We need it so that one input gives you one output, and an input never gives you more than one output. So long story made real short, if you plug in one x, you better only get out one y, or one output, one f of x value. So a couple of notation issues that we're going to deal with. Number one, we typically see functions as either y or f of x. So when you see them, when you see y equals something in terms of x, or f of x equals something in terms of x, they mean the same thing. They both stand for this function notation. Now we want to talk a little bit about what x means, what that is, and what y is, or what f of x is. So when you see that variable x, that input value, whether it's x or something else, the thing that you're plugging into, that input, it's called your independent variable. So in our case, when it says y equals some function of x, or when we're talking about a function of x, that x right there, that's what we're inputting. That x variable, that's an independent variable. Your input is always your independent variable. Why? What's that mean? Well, independent is kind of like what we want to be. We want to be independent people. We want to make our own choices. We want to self-actualize. We want to determine what we're going to do. We want to plug in our own stuff. And that's what the independent variable gets to do. So we get to plug into the independent variable. We say, I can put anything I want that makes sense. We'll talk about domain, the things you can plug in just a little bit. But really, we choose the independent variable first, and then the output, the y, the dependent variable, well, it depends on what we've chosen. You don't pick your output and then find the input that works for that. Not typically. Typically, we choose our x value. We choose what we want to plug in. We choose our input. We choose our independent variable x, and then our output is based on that. So when we look at our functions, y is in terms of x, or a function that's based on whatever this variable is, that's your independent variable. So in our case right here, what we're talking about, our input values, our x values, our inputted independent variable is x. So x, we call that our independent variable because you get to choose it. Now, once you've chosen, or once it's been chosen for you, once you've plugged that in, put an input or evaluated for that x variable, for your independent variable, whatever that is, that input, the function is going to churn something out. The function is going to take that one value and it's going to give you one value out. We call that value either the y value, or we call it an f of x value, or a g of x, or whatever the function is. We call it that value. So y, or if we're using function notation, f of x, I'm going to pause right here for a second. Please extrapolate from this. If your function's name isn't f, if it's like g or h, that's still an output value. So if we have a function with a different name, and we're going to talk about why we have different names for functions in just a little while. This lesson is just to get your feet wet on what functions are. That's why it's introduction. But extrapolate from this. So y values and f of x values, they mean the same thing, but if our function's a different name, we might use g of x or h of x, depending on what that function is named. Right there, that might give you a clue as to why we have function notation. Because if everything's called y, it'd be like everyone in the world being called Jim. You go, hey Jim, and everyone goes, yeah? And you go, shoot, man, we need different names. That's one reason why we have function notation. So you can call one function f and one function g and one function h or whatever. So back to this, if x is our independent variable that you're plugging numbers into, and your function is churning out an output, that's either y or a function name of x, depending on your independent variable. This depends. So this is not a chosen value. This is what you're given, your one output dependent on what you just plugged in. So this one you choose, this one you don't. That's why it's called the dependent variable. Now what's nice about this is together they make up an ordered pair. So when you deal with a function and you plug in a number and you get something out, well, wait a minute. Our input values are x's. Our output values are y or f of x, and this is going to give us an ordered pair, something that we can graph. Almost all of this class, I'm going to relate back to graphing and show you that this makes sense graphically. So when we're moving forward, we know right now, hopefully, that from what I said before, that we're going to be graphing functions. And without a functional relationship, one input gives you one output, it's very difficult to graph. So I've already covered the base, like, hey, we need functions because we can really only graph functions right now. So what's that allow us to do? If you have a function relationship, your independent variable, your x, your input, is going to be the first piece of information on an ordered pair. So it's going to be that first thing, that horizontal axis, whatever that is, x or t something. Your output is either y, or we could have x, comma, some function notation. Those are going to be the two standardly accepted ordered pairs that we get. Input, output. That's all there really is to it. So just a little 10-second recap to make sure you got it. One input gives you one output in a function. If that's not the case, you don't have a function. An input never gives you more than one output in a function relationship. How we write it is either y equals something with x's in it, or f of x equals something with x's in it, something with an independent variable, something you get to pick, to choose in, to put in there, and then your function gives you one output. We call the x our independent variable and y or f of x the dependent variable because it depends on what you've just chosen. Let's go through one quick example to make sure that you're really seeing it, that you're seeing what a function does. So you might have a job, maybe you don't have a job. A lot of our jobs in society work on hours. So the hours that you put in determines the pay that you get out. You guys know that. So if you work more hours, you typically, hopefully, get more pay. Well, in this case, I want you to think right now that what are your inputs and what is your output? Do you input $500 and then get to work 25 hours? If that's true, come work for me. I got a great job for you, all right? You pay me $500, I'll let you work 25 hours. It doesn't work that way. You put in the time, you get out the money. So you put in 25 hours, you get out something. So I want to make a little relationship here, and we're going to determine whether this is a function or not. So some guy works 25 hours and makes $500. Another person works 53 hours and only makes $310. At first glance, you might be going, well, that's not right. Well, do people have different jobs? Do you make the same rate as everybody else for doing different jobs? Well, no. Even in the same job, sometimes someone might have more seniority and make more money based on whatever the pay structure is. So don't be confused that this doesn't make sense, because it can make sense like that. Someone else works 30 hours and makes $490, and another person works 40 hours and makes $490. What I want to do right now is, number one, again, determine the inputs and the outputs, and you have to do that first, because what we're going to check next is, does every input give you exactly one output? So that's the only things you check here to make sure that you have a function. Don't add to that definition. So first are inputs. I mean, we'd be thinking, let's see, what's happening here? What are we doing first, and then what are we getting out of it? We're putting in our hours first. Our inputs are 25, 53, 30, and 40. In just a moment, because there really should be no suspense in math because you're learning, right? So in just a moment, we're going to call those inputs, the set of values that we're inputting into a function, we're going to call that the domain. The stuff we get out of it is called our range. So domain is a set of our inputs. I'll define that in a minute. Range is a set of our outputs. So one more time. We're looking at what we do first to get out something later. Our inputs are what we're plugging in first. Our domain, this set of x values, right here are our inputs. Our outputs are 500, 310, and 490. That's our range. Now, here's the only thing you got to check to determine whether this thing is a function. Look at your input and see if it gives you one output. So if I work 25 hours, do I make one value of money? Yeah, I make $500. If I work 53 hours, do I make one value of money? Yeah, I make $310. If I work, and remember, these can be different people. That's why they can have different rates. If I work 30 hours, can I make one value of money? Yeah, $490. If I work 40 hours or someone else works 40 hours, do they make one value of money? Yes, $490. This right here is a function relationship. Please don't get confused with a one-to-one function. Like I said, sometimes we know just enough to misinterpret things. What a one-to-one function is when you plug in one number and you get out one unique number. So in this case, this wouldn't be one-to-one because you get 490 twice as two different outputs. That's not the same idea as being a non-function. All a function needs is I plug in one number, I get out one number. I don't care if we get the same number out every single time. We could plug in like different inputs and get the same number on a horizontal line forever. So you plug in 5 and get out 10, plug in 7 and get out 10, plug in 50 and get out 10, plug in 1,000,000 and get out 10. So we can do that in function relationships. It's okay in a function to get out the same number twice, that's okay. The only thing, I promise, the only thing is one input gives you one output. This input, one output. This input, one output. This input, one output. This input, one output. Doesn't matter if they're the same. Think about maybe you and somebody else. If they're making different rates of money, could this guy work 30 hours and make that much money? Sure. Could this guy work more and still make the same amount of money? If they have different rates, that makes perfect sense. That's totally fine. This guy's just making a little bit more money per hour than this person is. Is that making sense to you? Stop right now and think if that makes sense, that this is certainly a function. One input is giving you one output. So right now what we have, that's a function relationship. And our inputs are 25, 53, 30, and 40. Our outputs are 500, 310, 490. And we're going to rename those in just a bit, domain and range. Now I'm going to change it. We're going to see if this is still a function. So let's say that we do all of this, we keep it exactly the same, and I add one thing. All right, tell you what, I'm going to do this. Right there. And so this guy's pretty happy, right? He's working 25 hours, he's getting 500 bucks. That's dependable. This guy's working 53 hours, making $310, no problem. This guy's working 40 hours, getting $490. He knows what he's going to get. Imagine being this person, and I'm not talking about overtime. I'm talking about where you're you've not agreed to a pay rate change. And so you work 30 hours and your boss comes to you and says, hey, great deal, man. I'm going to give you $490 today. You're like, woo, that's awesome. And then the next day he comes to you and goes, or the next week he comes to you and goes, tell you what, you work 30 hours, but I just feel like giving you $310. And you're like, wait a minute, what? And he's like, I just feel like it. And you're like, I'm not really happy with that. Why? Well, because you had an agreed upon rate, right? You agreed to work 30 hours to make that much money. What if he just or she just feels like giving you that much money? And what if you can't depend on it and you never know? Well, that's not a very good working relationship, is it? Because you don't know what you're going to get out for your work. That's exactly what a function has a problem with if you have more than one output for the same input. It doesn't know what you're going to get out of it. It's the same exact thing. It's working for you, right? The functions do some work. It needs to know what you're getting out. So this right here, this is fine, this is fine. Having two different inputs go to the same output, that's fine. This right here, having one input go to two different outputs, that is a no-go. That's a non-starter for a function. We're not going to deal with that in this class right here, but this would be a problem. This would need something to redefine the scenario, so to make it right. And so later on, we can do that in higher classes. Right now, you might say, well, this is a condition. Like here, you're making whatever per hour, and here you're making something different per hour, and it depends on the scenario. But as it stands right now, this would be a non-function. So we have inputs, we have outputs. One input gives you one output, no problem. We kind of went through this and said, when do functions happen? What do they look like? What's a non-function? Non-function is when this case is not met. When one input gives you more than one output, that's a big problem for us. So with functions, we have what's called a domain and a range. Our domain is a set of all the inputs, or all the values that the independent variable can take and get a real number out. Let me say that again for functions. We're not talking about imaginary numbers right now. We're not going to be graphing those on a real coordinate plane, okay? So what we're talking about for the domain is the set of these things that give you one of these things out. That's a real number. In other words, the domain is a set of all the inputs that you can have for a function. So right here, if we just want to relabel this domain, the domain is going to be the set of the inputs. It's just 25, 53, 30, and 40. That's what we're choosing to work. That's the hours that we put in. The range is the set of the outputs. or our y's, or the whatever dependent variable is. In our case, if we just want to relabel this range, our outputs are the range. So the range of numbers that we get is the 500, 390, and 310, 490. That's what we're talking about when we have the idea of a domain and range. Domain is just a set of inputs that you can put into the function and get a real number out. When we start talking about imaginaries, we're not going to be really talking about functions that are graphing for a while, but for graphical functions, functions that we're graphing here, and we graph those on a real coordinate plane. Our inputs is called the domain. The outputs are called the range. So inputs, x's, we jumble those together, group those together in the domain idea, and all the y's or f of x, g of x, whatever your function is, that's your range. I hope that makes sense. What we're going to do is we're going to come back with a few examples. I'm going to show you how to determine when a relationship, even an algebraic relationship, represents a function and when it doesn't. So I'll be back in just a second. All right, let's continue. So I have a few examples on the board, obviously, and we're going to determine whether these relationships, even algebraic, are functions or not. And there's some really easy ways to tell. Sometimes I'm going to make it so that's pretty obvious to you. So you look at it and go, yeah, that's not going to work. The key here is that with functions, one input gives you one output and not more than that. Let's look at these two first, just to get a feel for it. So right now what I want to do is look at the relationship S and look at the relationship R. And I need you to be able to pick out all your inputs and all your outputs. So when we're looking at S, remember inputs values are X values, are independent variable values. So our inputs here are -2, -1, 0, and 1. Do any of those repeat at all? So -2, -1, 0, and 1. There's no repetition. This can't I don't even care about the outputs, not at all. Because right now, checking functions is, does one input give you one output? If an input is not repeated, well, it can't possibly have a different output. So when I say -2, what's the output for that? It's 16. There's no other case where it's not 16. -1 gives us an output of 4. 0 gives us an output of 3. 1 gives us an output of 4. Every input gives us one output. Now, our output values here, the 16, 4, 3, and 4, oh wait, yeah, the 4 is repeated, but that doesn't matter. This would fail to be a one-to-one function, but it's certainly a function. It's just a very basic definition. One input gives you one output. If we're looking at something that just has a series of points, a sequence of points, then if our inputs are all different, we can't possibly have the same input mapped to two outputs. So for S, this is certainly a function. How about R? Think through it on your own. So just a little bit, think through. I need you to be thinking about what the inputs are right now. We should be checking those. So in your head, you should be reading through those inputs going, okay, it's this, 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 and this. Maybe look at the outputs, read through those 4 outputs and determine what those are. And then make a decision whether R represents a function or some other type of relationship. You should be thinking of it in your head right now. When I look through this and I see -2, 3, 5, and -2, go, wait a minute. -2 here is mapped to 5, -2 here is mapped to 6. One input, it's the same number, is giving us 2 different outputs. That's a problem. This is certainly a non-function because of these points right here, -2, 5 and -2, 6. Now, I've been asked the question before, what if that was a 5? Would it be a function? It'd be very awkward to write the same point twice. You wouldn't see it. But yeah, that would be, because this -2, 5, and if this number was a 5, -2 would still give you 5. So we'd look at that a little bit, but you're really not going to see that. The point here is that every input is not giving you just one output in these cases. These ones are fine. These two, not so much. This would be a non-function. I hope that's making sense to you. Now, unfortunately, we don't always get stuff like that. We typically get functions that are in algebraic form naturally. So, man, how in the world are we going to determine that? Well, there's a couple ways to go through it. And once we make it to these 2 examples, it's going to be pretty clear. So here's the idea. If one input is supposed to only give you one output, you can start by just plugging in a number to your independent variable, like x. So if you take and plug in something like 2, Negative 7 times 2 is negative 14, plus 5 is negative 9. Oh, hey, that's one number. You can try that, and that's a really good indicator that you're going to be plugging in one number all the time and getting one number out. Does it work all the time? No, it doesn't, because sometimes we can have non-functions where certain inputs do only give us one output, but others give us more than one. So it's better to kind of understand what's going on here. There's two things that you really look for, and they're really the same thing, but they come in two different forms. Number one, if you look at these four examples, these three are all solved for y, which looks pretty nice, and that's the best way for us to determine whether we have a function or not. So normally what we're going to do is choose to solve our algebraic equations for y, and we'll have a much better shot of determining whether it's a function. So this one looks really good. This one looks fine. This one looks, well, at least it's solved for y. It looks like crap, but it's at least they're solved for y. This one, not so much. So part of this is reviewing how to solve things for a variable, especially when we get to this one right there. I really need you to focus on that one. So when we're solving for a variable, we're undoing the equation, everything that's connected by addition, subtraction first, and then we're going to undo anything that's multiplied or divided. So we would do things like subtract 2x. And I'll do it from both sides, and we get negative 4y. On the right-hand side, negative 2x plus 8. Then to get rid of the negative 4, notice how it's connected by multiplication. We're going to divide, you just need to make sure that you divide every single term by negative 4. When you're trying to undo things connected by addition, subtraction, you're trying to get zeros. That's what we did here. We subtracted 2x because we wanted to get 0. Why? Because 0 minus 4y can give us that single term, negative 4y. It completely eliminates a term. When you're dividing or multiplying, you're trying to get ones. Why? Because if I get negative 4 divided by negative 4 giving us 1, 1 times y, it's an identity. That multiplicative identity of 1 is going to give us back the y. So we're going to be dividing by 4, actually negative 4, and we have to do it on all three terms. So negative 4 divided by negative 4, that's positive 1. That's what we're looking for because 1 times y is y. When we're adding or subtracting, you're trying to make zeros in equations. When you're multiplying or dividing, you're trying to make positive ones. On the right-hand side, there's some sign changes. A negative over a negative is a positive. That's going to be 1/2 x. Positive over a negative is a negative, so we think a negative term, we're going to translate that to a minus 2. So let's see, we've subtracted 2x, no problem. We've divided by negative 4, that's going to give us positive 1/2 x minus 2. Now all four of these equations are solved for y. They're in what we like, it's not function notation because we don't have a name of a function, but it's really close. It's how we typically like to see functions written, with the dependent variable equal to something in terms of the independent variable. Y equals something in terms of x. Here's what we're really looking for. We're looking for a notation issue that's going to cause us to have two inputs when we plug in one number. This doesn't have it. There's nothing there that's going to give us two numbers for everything we plug in. There's nothing here. Even though that's a power 2, that's not what we're looking for. If you plug in a number this and you square it, isn't that just one number? Plug in like 3. Well, it's 9. Okay, plug in negative 3. Notice you're switching inputs. It's still positive 9, but that's two different inputs you just plugged in. I'm not saying plug in two numbers and get the same number out. I'm saying if you plug in one number, is it giving you one number out? And the answer is yes. Plug in any single number here, whether it's 3 or negative 3 or 7 or positive 84, I don't care. It's going to give you one output. Are you seeing what I'm talking about? Plug in a number here, gives you one thing. Plug in a number here, gives you one thing. There's no notation issues that's uniformly going to give you two outputs for every one input. Here, the same thing. You plug in one number, you're going to get one number out. There's nothing notationally that's going to give you two outputs. This right here, that's a problem. And in general, man, that's what you're looking for. Something like a plus and minus, where when you plug in one number, it's saying, oh yeah, figure all that stuff out. Yeah, how about 0? Let's see, 3 minus 0 is 3. Square root of 3 is like 1.7 something, so this is a number. Oh, and then I take the positive version, and I take the negative version. That's two outputs, but I only plugged in one number. This is what you're looking for a lot of the time to determine whether you have a function or not. So function, yes. Function, yeah. Function, yeah, we solved for y to make sure it was easier to check. Yes. Function, no. This has a notation issue that's going to cause us to have more than one output for every one input. That's the big deal here. This is a non-function. I'm going to pause right there. Why? Have your attention. Don't miss this. Sometimes people like to not understand fully and misinterpret what I'm saying. This with the square root is a function. It's not the square root that messes us up here. It's the plus and minus in front of it. So that the square root here, the square root of 3 is the square root of 3, or if I plug in 0. But the square root of 3 is the square root of 3, but then I take the plus and minus, the positive, negative. That's the notation issue that we're talking about. Do you guys see the difference in that? This is fine. This is for sure a function. Plug in one number, you're going to get one number. It's the positive and negative that says for every choice you're making, I'm taking a positive and I'm taking a negative from that. This is the issues that we're generally looking for. So everything here is all good except for this one. This guy right here is the only non-function that we have. And I hope that I've made that really clear for you, that because of the plus and minus, that's a thing, that's a problem. Now think about it. Think about it right now. When do you have to put that on your paper? Do you remember? Like when you're solving stuff, oftentimes we'll have square roots given to us. And if a square root's given to us, it's fine. You don't put a plus and minus in front of it arbitrarily. You just take it for what it is. But when you're solving stuff and you get down to here and you go, all right, I have y squared equals x. And you go, how in the world do I get rid of a power 2? I'm trying to solve for y. And you go, oh yeah, I match the power to the root. So a square power would need a square root. And you put a square root around both sides, because what you do to one side, you have to do to the other. And you go, this is fantastic. Because a square root cancels a square power. They're inverse functions. That's a power 2. That's a root 2. I get a y. On the right-hand side, I get a square root of x. And your teacher goes, and I go, no. You stabbed me in the heart. My little black math heart is hurting right now because that's not right. You see, in order to maintain the idea that when you square a number, whether it's positive or negative, you get a positive number out of it, we have to have a plus and minus in front of that square root. So here's the idea. What I always tell my students is this. When you're the one who puts the square root on the paper, which stems from, I'm solving something from a power 2. When you're the one who does that, takes a square root on both sides, you have to put the plus and minus. Long story short, if the square root's given to you, you don't need it. If you're solving for a square root, or solving something that's squared, and you take a square root, you have to put that plus and minus. That's a big deal. Not for a cube root, not for an odd root, but for even roots, yes. Now, can you extrapolate from that? Can you look through these last 3 examples and think about when we're going to have a non-function or not? So take a look at it. Remember what we're going to do. We're going to look at these and go, hey, I have it solved for y. Oh, this one I need to solve for y. We're going to solve all of them for y, and we're going to look at our result. So think about it right now. If you go through the process of solving this for y, are you going to have to take a square root? If the answer is yes, then you're going to have a plus and minus. And right there, it's going to tell you, yeah, that's not a function. Right here. When you solve for y, are you going to have to take a square root? And the answer is no. No, there's no y squared there. I'm not going to have to take a square root. Therefore, I can't have a plus and minus. That is going to be a function. How about this one? Think through it for yourself and go through the process in your head of solving that for y. When you get down to the end, are you going to have to take a square root? And the answer is, yeah, I'm going to. So if I'm going to have to take a square root on both sides, I'm going to have a plus and minus. That's not going to be a function. Let's go through and see that in action. So when we're looking through it, we're going, all right, man, now that I know about square roots, and I know that when I take them, I have a plus and minus, which is yielding 2 outputs for every input, this is probably not going to work. Now we're going to practice for fun so that you get good at solving for a variable. But we're going to subtract 2x squared on both sides. By the way, the reason why we're doing this right now is to make certain that we're not making little bitty errors when we're solving things. For instance, we cannot take a square root right now without getting rid of that 3 in front of the y squared. Don't do it. I see it all the time. I see people try to take a square root. It doesn't work because that power 2 is associated only with the y and not with the power 3. There's no parentheses, and therefore you can't distribute that power 2 onto that coefficient. So we divide by 3 and get something kind of awkward. really, who cares if it's a fraction? We're just seeing if it's a function or not. And we end with, oh, there it is. Y squared negative 2/3 x squared plus 1/3. Is that solve for y? No. No, solve for y means I have y by itself, no powers, no coefficients, no nothing around it. So when we solve for y right now, we're going to have to take a square root. We have to match the power of the root. We have to do it to both sides. And as soon as you put a square root on your paper, wasn't there before, you're the one who did it, you need a plus and minus. You don't need it on both sides. That's redundant because we would have the ability to get both the positive and negative whether we do it once or twice. On the left-hand side, we need just y. On the right-hand side, we have a square root. We have a whole bunch of garbage inside. But right here, that's the problem. This right there is telling us that we do not have a function. It's not a function because every time we plug in one number, it would automatically give us 2 out systematically. That's the issue. I hope that's making sense. Right now, I think I'd like you to do this one on your own. So if you want to pause the video and try that, give that a try right now. So see if you can just look at it and tell me it's not a function, and then see algebraically what's going to happen when you solve that for y. So I'm going to start it now, but you should be pausing the video and trying that. So for us, we're going to subtract x squared, no problem. You could, of course, add 4y squared and subtract 1. That's the same thing. We're trying to make zeros when you add or subtract. So 0 minus 4y squared is negative 4y squared. On the right-hand side, we have negative x squared plus 1. Before we take that square root, I know I'm going to have a plus and minus. I know it's not a function right now, but before we show that, we're going to divide everything by negative 4. When you divide, we're trying to get positive 1 on the side that we're trying to solve for a variable. So negative 4 over negative 4 is positive 1. Positive 1 times y squared gives us y squared. On the right-hand side, a negative divided by negative is a positive. So you can write that as x squared over 4 or 1/4 x squared. It really doesn't matter. Minus 1/4. So we're adding a negative now. Lastly, we're going to take a square root on both sides because that's not solved for y. So when we do that, square root, both sides, the whole thing, I have to do a plus and minus. It's solved for y, that's good. But when we do it, we have this expression that's not a function, this statement that's not a function. It's a relationship. It will give you numbers when you plug something in, won't it? So if I plug in something like 1, okay, this is a great example. If I plug in 1 right now, or if I plug in negative 1, do you see how it would only give me one output? Do you see that? So if I plug in 1, 1 squared is 1, 1 over 4 is 4, 1/4 minus 1/4 is 0. It's okay to take the square root of 0, it's just 0. And plus and minus 0, well, wait a minute. You can't have both positive 0 and negative 0 to make sense. It's just 0. This is what I'm talking about, how you can kind of get screwed up if you just pick a number to plug in. Because if I plug in the number 1, or even negative 1, because negative 1 squared is 1 also, then it's going to give me only one output. And I might make the mistake that this is a function. It's not. It's systematically taking every other value besides that and giving you 2 outputs. So don't fall into that trap. That's why we talked about how you can check a lot of times by plugging a number in, but really we want to understand, not just go through some process and plug a number in, but really understand what's going on. That's a non-function because for almost every input, it's going to give us 2 outputs. Lastly, that, even though it looks weird, is going to be a function. It doesn't have a y squared. There's no square root up there with a plus and minus in front. We're not going to get one. But I want to go through the process of solving for y to set us up for a couple things. When we get to exponentials and when we get to solving inverses, which is much, much later, we're going to have to solve this sort of stuff for a variable like y. So one idea behind doing that, when you have y's on multiple terms, here's the thought process. Stick with this because this is a big deal, okay? What I need you to do is get all of your terms with y on one side, get all of your terms without y on the other side. And that's set up right here. This has a y, this has a y, and these 2 terms don't. So out of the 4 terms, the 2 that have y's are already grouped, the 2 that don't are already grouped. Now, why would we want to do that? Well, if you group all the terms that have y's and all the terms that you don't have y's are on the other side of the equation, you can factor it. So the idea behind solving for something when your variable you're looking for is on more than one term, group your terms with that variable on one side and all the ones that don't have it on the other. Then factor that variable. What factoring does, it creates something that's being multiplied. Do you remember that? We divide out and create a multiplication problem. So if we group our y's, factor, and then we can divide. So we've already grouped our y's. Since they both have a y as a common factor, we're going to factor it. That gives us just x plus 2. We're removing that y by division. And lastly, because that's multiplied, because that's what factoring does, gives you stuff that's multiplied together by going through the process of division, the opposite of distribution. Because that's multiplication, we can divide both sides by x plus 2. And get y equals 3x minus 1 over x plus 2. Now you can try it. Plug in a couple numbers if you want to. It's going to give you one number out. But the main thing to notice is there's nothing awkward going on. There's no notation that's going to systematically give us more than one output for every input we plug in. I hope that this has made sense for you. I hope that right now in your head you have the following things down. Like you understand what a function is. And you could tell me either algebraically, with points, or with even a real-life relationship, what is a function and what is not. You need to be there. You didn't know that there's some notation that systematically causes non-functions. The last thing that I want you to do is be able to solve equations for a variable, especially stuff where we might need to factor or take a square root with a plus and minus. You should have sort of a decent idea of domain. So we need to kind of associate domain with inputs, x values, and range with outputs, y values, f of x. But I'm gonna explore that more in a couple of videos. So hope that makes sense. Hope you're doing well. I'll see you for the next video.